And to talk about hash tables, we have to talk about arrays. And to talk about arrays, we have to talk about memory. But before we jump into that, one other thing I just want to give everyone a heads up. My internet has been a little wacky over the past few days, and I've got someone coming to look at it today. So if I vanish, I will be right back. And I don't think that should happen, but just in case, don't run away. I will return very quickly. I do have a backup internet option. Also, someone is unmuted, and that shouldn't be possible. Curious. Very interesting. All right, let's learn some stuff. So we talked, if anyone remembers the distant days of 2 weeks ago, when we talked about linked lists and arrays in memory, we looked at this. Does anyone remember this? We're looking at the bucket level. These are arrays. These are our linked list here. Does this look familiar at all? I hope so. I believe, actually, speaking of internet errors, I'm remembering that Google Sheets went down when we did this. So what we're going to do now is we're going to go deeper. We're going to zoom in to another level where instead of each of these cells representing a bucket, we're going to have each of these cells represent the lowest level. What's at the bottom here? If I zoom in now and I open up a magic window into my computer's memory right now, what is every single one of these squares filled with? Bits. Lucas has it. And thank you, Desiree. I'm glad it did, and I hope this does too. What does every single one of these have, no matter what? It must have something. Cannot be blank. It cannot actually look like this. A 0 or a 1, or a 1 or a 0, or some zeros, and a 1. Everywhere. And I'm not going to do that. I'm not going to fill all of these because it would be distracting. But keep in mind throughout all of this that every single one of these blocks is filled with something. And that could be, again, all of the silly examples that we have on this sheet. These could be zeros and ones representing zebra or purple or the smell that happens after rain. Anything that we can represent in data ultimately is represented at the very bottom, at the lowest level that you can go, as a 0 or a 1. Or if we want to get literal and look at the hardware, what does that actually represent? Does anyone know? Charge or no charge? And even really particularly specific, it could be, if you're looking at a hard drive, it could be a signature above or below a certain threshold. Yeah, Matthew has it. Charge above a specific threshold. Because things get funny when you get that small. When you fit billions of something into something about the size of your pinky, the world is a little different. But we don't need to worry about that part. For us, we're working at the software level. And at the software level, the smallest, the most granular, the most specific that you can get is 1 or 0. And it must be 1 or 0. It cannot be something else. So if we say that this represents, again, the smell of the air after it rains, how do we know that this is in memory? What is the word that tells us that this piece of memory is being used? Lots of people are typing. Good. Everyone is awake on a Monday morning, early. Well, early for some of us, it's mid-morning for others. Allocation, yeah. Thank you, Andrew. So this is allocated. Somewhere, depending on the architecture, there is a list that says that this piece of memory is in use. Want to know something really trippy? Where does the list of what memory is in use live? Memory. So somewhere else in memory, there's an area of memory that's reserved to tell you, or to know and tell itself what memory is used and what memory is not. Does it list itself? So it's in the architecture. It's basically pre-allocated. Yeah, it's recursive. It's ones and zeros all the way down. So if we delete the smell petrichor, the smell of the air after rain, what happens when we delete it? How does this keep happening? Zoom is being twitchy today. Coded in ROM, the pointer gets deleted. Getting close, thank you, Sean. But all that happens is it gets deallocated. It's still there. The same ones and zeros are there because there's no reason to do anything to them. It's just marked as now free and available for use. So eventually, when we try to allocate something else, then we can reallocate the part that we need for something. So let's do some counting. Trick question. Maybe not a trick question. How do you write 1 in binary? Kind of a trick question. 1 in binary. Thank you, Ty, for being literal. Thank you, Sandy. Some of you are thinking about allocating it as a integer, which is cool. A lot of ways to do it. There's a lot of ways to do it. Those are all largely right. How about 2? 2 is a little trickier. Yeah, 2 is 10 in binary. So counting in binary is 1, 10, 11, 100, 101, 110, 111, 1000, 1001, because it's base 2 instead of base 10. Which reminds me, I always share my favorite binary poem. Which, if you read that out, 1 1 was a racehorse, 2 2 was 1 2, 1 1 1 1 race, 2 2 1 1 2. Little binary fun on Monday morning. All right, how about an integer? Some of you, in your defining what 1 is and how it's written down, we're close on that. How would you write an integer 1 in binary? Why couldn't the computer have had 10 figures too? Would have made things so much easier. Nick, that's fantastic. It's a binary program like a Heroku, Zach. You guys are on fire today. That's great. So yeah, so Sydney has it. Why are there so many zeros? Why do we need so many zeros to just write 1 in binary as an integer? Why is that? What's the point of doing that? Because it's allocated memory space. Because, well, why do we do that? Why don't we just allocate less and then make it bigger when we need it to? Yeah, you need to know when to stop reading the bits. And that's what it comes down to, is it's how you read it and how the computer handles it. Is it needs to be predictable for the computer. You have to tell it, there's a number here, read these many bits. Because, well, let's do this. So an integer has how many bits? It's different from different languages too, but your standard int It has 4 what? Bytes. And a byte is what? 8 bits. 2 nibbles. So there used to be a data type that we don't really use very often anymore unless you're doing embedded programming. Like if you're programming the computer that lives inside a modern toaster, which everything, the Internet of Things, everything not only has computers, but it's attached to the internet. If you're programming a toaster or refrigerator or something where hardware cost becomes more significant and things get smaller, there might be a short integer. Has anyone encountered that before? Done some C or C++ programming? So what's a short? Opposite of a tall. Fair enough, Michael. And thank you, Jason, Matthew, Stephen, and Blake, and Jason and Jorge for the answers. Nisa as well. Lots of participation today. So yeah, it's a 16-bit integer. It's smaller. And also, again, it depends on the specific language and the specific implementation of the language. You should not take these for granted that they're a specific size, which can get important if you're doing like network programming or something and you're reading a byte stream. You need to know how many bytes to read. But we're going to do, with this exercise, to keep it on the screen, we're going to do a super short. My own data type, it is 4 bits long. So it's an integer value, it's 4 bits long. So let's do some counting again. In my super short integer, how do I represent 0? All right, yep. 4 bits, all 0. And then 1, no tricks here. And then 2. Then 3. Let me know if I screw up. I'm terrible at counting in binary. If you think that this is hard, you're not the only one. I learned that I was not suited to be an electrical engineer when they told me to do on paper. Oops, no 2s there. It wasn't that hard. When I needed to do, in using long division, this number in binary divided by this number in binary on paper, I said, this is not the right thing for me. I'm not going to do hardware. I'm going to do software. Okay, so let's keep counting. We're up to that, right? Okay. So we said this is 0, this is 1, this is 2, this is 3, this is 4. Okay? So if I say, again in pseudocode, if I declare a variable and I say my super short becomes 4, what happens? What does the computer do? At the memory level. Allocates memory to hold 4, right? So let's grab some space here. This looks convenient. Or we could even grab this space. Remember, it doesn't matter that there's stuff here. There's already stuff everywhere. Again, we're not drawing it because otherwise it would get really confusing with 1s and 0s everywhere. But there's stuff everywhere. This part is unallocated. So even though there's stuff there, we don't care. We're going to grab it, say it belongs to me now, allocate it, and then what happens next? We overwrite it. So we say, well, how about this one here? This is what 4 is right here. There's already a 0 here. So what do? Do we do anything here? No, we do. Kind of a trick question, but we overwrite the 0 with the 0. At least conceptually, as far as we're concerned. We can't make that decision, and it would be just as much work to evaluate an if statement as it would be just to put whatever's there. So we overwrite this one, then we overwrite this one, then we overwrite this one. All right? So what is actually in my super short? What is this? What data is there? It's a pointer. To O2. What else is in here? Or to Q2, sorry. Might be a little hard to read. So it's a pointer to Q2. What else is in here? What other important information is in here? Type, which is super short int, which means to access this, if I say print my super short, what are the instructions to do here? What is the computer told to do, the processor? What's the machine instruction? Let's go to Q2, read the next 4 bits, and interpret those as a super short int, which will then print 4, because it'll convert it to decimal for us, deep down in the bowels of the machine language stuff. All right? So that's pretty straightforward, right? But what if I want to say my super array equals this? What do we have to do here? Dance, monkey, dance. Allocate the length of the array with the data for 2. Yeah. So we find a spot that we're not using. This one looks good. And how many do we need? We need 8, yeah. The length of the array times the size of the data type. So we get 1, 2, 3, 4, 5, 6, 7, 8. And we allocate them. We say, this is mine. Now, are these blank? Remember, they're not. There's stuff in here already. Could even all be zeros. But zeros are still what? If this was all zeros by happenstance, what does this still represent? What is still here? It's a value, it's data, it's interpretable. But my array, does my array have anything in it? If I say print my super array 1, what's going to happen? Maybe. Samuel says index out of range, and it might. But only if what? What needs to happen for index out of range to happen? Well, resize might be what we do to respond to that, Nicholas. You're on the right track for a task we're going to do later. If space was not allocated, we're kind of circling around it. There needs to be a counter to see if an item is in the array. Absolutely, Jason. So Jason's getting closer. What needs to have happened at some point in time for this statement to generate an error instead of printing 0? Yeah, the implementation says to only return if assigned. So what needs to have happened is someone at some point in time needs to have programmed this functionality to be there. And if no one has programmed this functionality to be there, then it won't be there. And there are some languages and some implementations of different languages where if I do this, do you know what it'll do? It'll say, all right, you're the boss. I trust that you know what you're doing. Whatever you say, I'm going to start at this pointer, I'm going to count, and I'm going to return that. So all of these things that are here are only here because someone programmed them. And so that means, you know, if you're working with a linked list, for example, and you want the length, that may or may not be there depending on whether or not it's included in this implementation of a linked list. Often it will be because knowing the length of something is useful, but you can't take any of this for granted. Every single thing that you call .append, which let's call that now. If I say my super array .append, let's put 1 in it. What do we do? Yeah, absolutely, Andrew. That's why it's possible to recover erase things. But what do we do here? What do we do first? There's an equation for this. For everything with an array, there's an equation that the computer does. Here, let's change this a little bit. Let's not get into append just yet. Let's say my super array at index 0 becomes 1. What do we do to find that? Stephen has it. Thank you, Stephen. Index times size of type plus the starting address. So I like to think of it the other way around as we go to the starting address, which again, my super array itself, what is my super array equal to? Not with any sub number, just my super array is what? No, well, it's a size of 2, Sydney. So you're close, but it's just a pointer. It's a pointer and a data type. So it's H10. So following Stephen's equation, I go to H10 and I look at the size of type, which is 4. So these 4 bits here, and then I change them to the new data that I want them to be. So I overwrite 0, 0, 0, 1. What else do I need to do? What do I need to store in the array? We need to know that this part is in use now, right? Yeah, so Matthew, my super array equals X. This is a way of allocating an array with 2 spots. So it is size 2, which brings up a good question. Is this possible? Yes or no? I'm going to do array 2 equals that, or becomes that. Does this actually exist? Is this something that the computer can do? Sorry, Sydney, this is a trick question, or at least a tricky question. It can't. Because it's ambiguous, and computers don't do ambiguity. So what happens is Jason has it, it pre-allocates whatever the minimal or default memory size is. Perfect. So now let's try append. Where does it go if I say my array, my super array, the original one, the blue one, and let's append 3 to it? What do we do? Add 3 in the allocated space, Sydney. You're definitely on target, but remember, we're a computer. We have to do it one at a time and very precisely and very specifically. So first, what do we have to find? What do we need to know that we haven't talked about yet? What's used and what's not used, right? So we have the allocated amount, and then we have the in-use amount. So we go to the end, which is here. Nope. Here, the unused space. And we put in our 3, 0, 0, 1, 1. What else do we have to do then? Got to mark this as being in use as well. So what do we have to do now? I could just append forever, right? My super array append, let's append 4 now. Oops, that should have been a parenthesis. So let's append to 4. What do we do? Uh-oh. Can we just grab this space right here? No. This might belong to someone. This is already in use. And remember, there's always data here. So what do we have to do? Create a new array and copy the previous data. All right? So how do we do that? Remember, step by step, we're a computer. One step at a time, very precise and specific. So find new space. All right? How many blocks are we going to take? How many should we allocate? Let's double it. We need at least 3, but Jason has a good idea with doubling it. Why is doubling it a good idea? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because binary likes doubles. That's a fair reason, I suppose. And because anticipate growth. What's more expensive, processor time or memory? Processor time. So what is the runtime complexity of the operation of doubling the array every time we run out of space? How frequently will we do that? We're getting there. So well, let's think about it. So let's start out with an empty, with one space. Emma's got it. We have one space. We fill that up, so we have to double it. Now there's 2. We can put 2 things in there. Or one more, and then we have to double it again. Now we can put 2 more things in there, and we double from 4 to 8. Then we put 4 things in before we have to double again. So it takes twice as long each time before we have to double it, which means it's log n, which is very good. But as many of you are probably thinking of, the other thing that we have to do is we have to copy it over. And that takes computing time, because what do we have to do? Can I just do this? I'm just going to grab all of these right here, and I'm going to copy them all at once, and I'm going to paste them all at once. We're done, one step. Nope, can't do that. Computers are linear, one at a time. So I have to go 0, then this one is 0, then this one is 0, and this one. All right, I won't keep that up for the whole one, but we have to do have to copy it one at a time. So then 0, 0, 1, 1. Oh, and I wanted 16, didn't I? Let's grab those. And then we add our new number, our 4. So 0, 1, 0, 0. And all of this is marked as in use. And this is allocated but unused. And again, what's in here? Thank you, Andrew. I'm glad. What's in this last spot here? Whoops, is it empty? Old data, who knows? Could be anything. Could be a piece of something. We don't care. Belongs to us now. And we've got more space. But what else can we do from an array? What did I tell you that linked lists are great at and arrays are not great at? Insert, or what's the opposite? Insert is right, but we're going to demo the opposite, pop. So if I say my, oops, I don't mean to scream at you, my super array dot pop, and we take the item out of the beginning, what do I have to do? Oops. Shift them all over, right? So we're going to first go to the index, count the size over, and return this. So we'll return our 4 bits here, and then we have to copy over starting from here. So we go 0, 0, 1, 1, 0, 1, 0, 0. And then what happens to these 4? Do we delete them? Nope, just mark them as used, unused. Jason has it. Thank you, Jason. So it's unused. Well, let's undo that. Let's go back. Pretend we didn't do that one. What if I want to pop something different? What if I say my super array dot pop 1, the first indexed element? That would be these 4 here. What do I have to do? Yeah, we have to shift everything. Because why can't I just do this? Why can't I just say, oh, we're not using this part anymore? Because arrays are contiguous. And this is why arrays are contiguous. Because what happens if I say for I in range 0 array size, print my super array I, what's going to happen when it gets to here? It's going to print it. There's still data there. There's no way to say that this isn't data. Because again, what is my super array? All that's in there is a pointer and a data type, the size of the data. So there's no way to know that this isn't in use. And that's why they must be contiguous. Because again, what's that equation? If I want to say print my super array 1, what do we do? What was that equation again? Yeah. Starting address and then index times the size of type. So the starting address is C12. The index is 1. And the size of is 4. So we start here, we count over 1, 2, 3, 4. And then what do? Then we read what? The next size of type bits, which in this case is 4. So we read 1, 2, 3, 4, and we interpret those bits as a super short integer, which is what? In this case, what is this value here? It's 3. All right. So what does this mean? What has annoyed you since the first time you've worked with an array that's been confusing and causes all kinds of errors and bugs and irritation and frustration? And that's a great question, Emma. We'll get to that in just a second. But what property of arrays has bothered me since the beginning and probably bothered all of you? That's really confusing when you're first starting out. It's 0 indexed. But do you see why they're 0 indexed? It's because of that equation. If we do my array times 0, then it's go to 0 times 4 plus the address, or the address plus 0 times 4, and then count the next 4, which are these 4 right here. And they could have done it the other way. They could have said, made the equation, and then add, go to the index, and then, depending on how you do it, add or subtract that number of bits. But then what would that mean? It would mean every single time you look something up, you're doing another piece of math to make it 1 index instead of 0 index. All right. Emma, that's an excellent question, and that's actually what we're going. So there's 2 answers to that question. One is the more general sense. How do I say that I'm deleting this? And that's, which by deleting it, I say I'm just deallocating this. And that has to do with how the computer itself allocates and deallocates memory, which we'll learn a little bit more about in architecture week. But the short version is there's literally just a list of, the first segment of memory is made up of a list of what memory is in use and what memory is not. And there's just a percentage is reserved. And it's like getting into like the BIOS knows where to read to look for that to see what's allocated. But the other version of that question is, how do we know in our array what's going to be done and what's being used and what's not. And that's what we're going to do right now. So let's do some code. So open up the file for the week, and you will see that we do not have a folder in here for arrays, and we do not have any starter files because together we're going to do it from scratch. All right. So we're going to say dynamic array, make a folder. Inside that folder, we'll make a file called dynamic array.py. It's up to you if you want to spell array wrong like I did, or if you want to spell it correctly. It'll work both ways. You just have to remember what you've done and be consistent. And Matthew, you think that that's crazy? One of the hardest things about game programming is that in game is trigonometry, and not just because trigonometry is hard, but in game libraries, 0 degrees is almost always north. And in math libraries, 0 degrees is almost always east. And you have to use both to do anything. So you're always translating and rotating things 90 degrees or minus 90 degrees, and it's painful and hard. But it's fun. All right, we should all have something called dynamic array. And we're going to make a class called dynamic array. And what do we need for every class? What's the first function that we define? Init. We need the constructor. In this case, we're going to have self and capacity. And what do we need to do for capacity here? What did we learn that is mandatory when you're declaring an array at a low level? Can I declare an empty array? Nope. Have to have a default size. So let's give it a default size of 8. And then Emma's excellent question. We need to keep track of how much we're using, which starts at 0 because it starts empty. And again, we have our capacity. And here's one thing that is a little bit contrived. And because we're doing a low-level process, we're programming our own low-level implementation of an array in a very high-level language, we're going to have to do something slightly silly, which is we're going to make space for our storage. And we're going to say none times self.capacity. So what am I doing here? What is this doing in Python? Yeah, we're pre-initializing this many blank spots in an array. So we're making 8 empty buckets to put stuff into. And because Python doesn't give you low-level access to this kind of stuff, we're actually using a Python list to, which is what? What is Python's list? Because as Michael says, we don't get access to raw memory. So what is a list in Python? It's an array, and more specifically, thank you, Jason, Sandy, and Allison, it's Python's implementation of a dynamic array. And Matthew, if you want to really dig into it, it's an array of references and how Python manages memory, and everything is actually a name, and everything is immutable, and all of that stuff. Is there a difference in implementation between self.storage equals none times capacity or none times self.capacity? No, not really. There might be, like, if you look at it with a microscope, specific differences in how it executes things Jonathan, but the end result will be the same. It's one of those things that has to be one way or the other. All right, so we have our array. What's usually the first thing that I suggest that we program with these sorts of things? And kind of the first thing that you have to. You don't really have much choice in this one. Lots of people are typing. I love it when lots of people are typing. Append, you're very close, Nicholas, and you're on the right track. We need to be able to put stuff in here. And there's two possibilities that we have for this. What's the other possibility? The first thing we need to do is put stuff in the array somehow, right? And the two functions traditionally that you do with that, Nicholas has one, which is append, and Ty has the other, which is insert, which is, yeah, John, you're absolutely right, but it's the only way we can do it. We used to do this in C, and you could allocate the memory on your own, but such is the nature of life. So this is where we can use ooper, okay? We've spent all morning doing the first step, understanding how all of this works. And there's room for some planning here. Because append and insert both do the same thing, more or less. They put stuff in the array. But what is one way that we could think of or define append as being? What could we potentially use? Yeah, insert at the end, right? So I think that we can plan this and be a little bit clever. And if we write insert first, that will have the power to insert at any index. Then we can write append to make use of insert and save ourselves some time and make our code what? Drier, right? That's why we write functions, so we could use them repeatedly in different circumstances when appropriate. So insert, we need self. What are the two arguments that we need to insert the value? I just said one, we need the value, right? And then we need the index. Where are we putting this? But before we can do this, there's a couple of things that we need to check for. What do we need to check for here? What could go wrong? And remember, what do we want to do in a high-level language that helps the user out, helps the programmer out? Yeah, if it's at capacity or if we're out of bounds, right? So we'll say if index is greater than or equal to what? Self.count. What do we need to do? Well, we can handle that later. To do better error handling. And for now, we'll just print error index out of bounds. Isn't count the index that we're at? Tricky question, Jason. And this is why arrays are confusing and it's so easy. If I have one item in my array, just one item, my count is 1, right? But where is it? What index is that item at? It's at 0. So if I try to put something at index 1, remember we're inserting. And inserting is replacing a value that's already there. So if I try to insert at index 1, that's out of bounds. That's not being used yet. We might have the capacity for it, and it might be appropriate for an append, but with insert, remember, insert, we want to make sure that if we had this here, we don't want to accidentally insert over here, right? Because again, that breaks the array because they have to be contiguous because there's data there no matter what. So there is data in that array, whether you like it or not. So we want to make sure that we don't put it out of range. And that's where that error out of range comes from. We have just created it. We have decided that this is a feature that should exist in our data structure. Features aren't always things that you make to meet a design that a designer made. Sometimes a feature is a thing that's useful for other programmers or yourself. All right, otherwise we're good. Jonathan, again, great question, and Mally as well. And because if self.count is 1, then our one item in the array is at index 0, and index 1 is past the array. So again, right here, it would look like this. So count is 1. We have this one item here, but it's at index 0. So this is out of bounds. Great question. Thank you for asking, Mal. Well, we want to insert at 0, right? But if we call it insert 1, we want 1 to error. Well, right now 0 will error because we don't have anything in it. So we're planning ahead, Michael. A good point. So what do we need to do to make space then? If we're putting it at some random spot in the array, what do we do? Let's say we had this right here. So let's pretend there's already something there. Again, it's kind of planning ahead. What do we have to do to these numbers here to insert something new at 0? We have to shift them, and one at a time. So we take the 1 and put it here, and then the 0 and put it here, and then the 1 and the 0. But at the bucket level, we just shift the whole bucket. So we can say for I in range self.count index and -1. So what are we doing here? What kind of for loop is this? Yeah, I do that every single time and I don't know why. Yeah, it's going backwards. So we're going to the end of the array and we're moving everything to the right. What else might we need to worry about though? What are we taking for granted here? That there's free space. So let's put a quick check for that too. If self.count is equal to self.capacity. Then we can do a to-do here as well. To-do increase size and print for now error array is full. What's the other thing that we need to do with these functions that I'm forgetting to do because that's what it is? We need to return out of them. All right. Then the last thing that we have to do for our insert is insert our value. So self.storage at index becomes our value. And self.count plus equals 1. All right, let's take a break here. When we come back, we'll do another method or two for the array, and then we're going to talk about hashes and hash tables. If you have any questions, think of them and ask them, but then make sure you stretch your legs because that's important. And if one of the section leads could please do the timer and the soothing music so I get a 3 on my rubric for today, I would greatly appreciate that. See you all in a minute. Alrighty, everyone. Welcome back. Hope you had a good break. Yeah, Emma, one of the things that you learn about working in video games is the astonishing amount of times that you are lied to by the game and the game systems. And what you think is true is actually something very carefully curated for you to think is true, but may or may not be actually the case. One interesting thing is that for American gamers, you actually have to lie to them about the odds of success. And this is why tactics games sell so poorly, because a Japanese gamer, if you tell them that they have a 90% chance of success of something and they fail twice in a row, they'll be sad that they were unlucky. An American will be confused and outraged that the game is cheating them. So you have to adjust what you tell them for expectations. Anyhow, but we are not talking about games today. We are talking about arrays. So we've written our function for inserting something. How can we make use of this for append? Self, we don't need an index, right? Because we know where it's going. We just need the value. What could we do here? Check if the array is at capacity. That's good. I'm going to copy and paste this. I'm suspicious, but I think here it's not really, what's the opposite of dry, wet? It's just one little check. But then we should be able to just increase the count and insert. So self.count plus equals 1. And then, we might not be able to be clever here. What's the problem with that? That was my first thought as well. Self.insert at self. Uh-oh. How do we get the length? Yeah, it'll increase the count multiple times while appending. So what should we do here? What would you do if you were in this circumstance? Thought it might work, thought we could be more efficient. Self.storage, self.count equals value. Yeah, that might work. Let's do it that way. So we still need that. So say self.count plus equals 1, self.storage, self.count equals value. So we've increased the count. And then, oops, what do we need to do though? Is this going to work like this? Or what is this going to create? I'm doing it in this order. It's an off by 1 error, isn't it? So we need to do -1 here to account for it being 0 indexed. All right, so sometimes you do some planning and then you have to reevaluate your planning. You start to do it and realize it doesn't work. And yeah, Jonathan, the other solution would be we just flip line 30 and 31. So instead of doing it this way, here, let me do this. It would also be just fine to do it this way. All right. And one last thing that I want to do real quick. We're a little behind time. Yes. It should be in training kit, Michael. And if not, could someone else please paste it? Thank you, Ty. So the last one I want to do real quick, we're going to go through this quickly, is we do need to double the size, right? So how are we going to do that? Define double size self. So we're doubling it, right? So self dot capacity times equals 2. Make the capacity twice as big, right? Then what do we have to do? And I guess we could just say, well, actually, no. We need to make what? We need to make a new home for this stuff, right? We need to allocate new memory. So we need to make a new array. New storage is same as we did before, none times self.capacity. Then what do I have to do? Other than fix my typo right here. Thank you, Andrew. Beat you to it. Well, that's fair, Colin. But what's going to happen if we say self.storage equals new storage? That's just going to make it empty, right? We're going to erase everything. So what do we have to do before that? What did we do in Google Sheets? We got to copy the values over. And because we're doing an exercise where we're doing everything manually, we're not going to use any Python functions for that. We're going to do for I in range of self.count, new storage I becomes self.storage I. So what's the runtime complexity of this operation here? Oh, then, but wait a minute, isn't the new one twice as big? Doesn't matter. Oh, then you've all got it right. So then, tricky question here, very tricky question. What is this line of code doing? What is actually changing? Is it writing over self.storage, Derek? That's a natural thing to think. And at the surface, it's what it looks like, but it's not really what it does. It's reassigning the reference. Amanda and Gustavo have it, and Chris. We're changing the pointer. So going back to here, we're just saying that my super array used to be a pointer to H10, and now it's a pointer to C12, the new location. And then also as a part of it is it deallocates the old one that we're not using anymore. Also happens as a part of the assignment. In theory, depending on the specifics depend on the exact language and implementation. But generally speaking, that's what happens. All right. We're going to stop here with arrays. Or what questions do you have about them? So the old storage becomes garbage. Absolutely, Emma. And eventually, with a memory managed language, eventually it'll notice that nothing is referencing that anymore, and it will get garbage collected. Were we doing this in C, we would have to ourselves manually deallocate that memory, or we'd cause a memory loop. So what is a hash? Other than a delicious breakfast item. Which, funny enough, what is a hash the breakfast item? We could start that way. That could be our introduction. It's getting close to lunchtime, might make us all hungry. Potato encrypted string. So hashes are often made out of potatoes, like hash browns, but a hash is a breakfast item that's just made by chopping up a bunch of stuff, mixing it together, and frying it. And put it back together again. Absolutely, Laura. That's a good way to put it. So how about, though, in computer terms, we've heard of hash before. We might have used one before for different things. It's often related to encryption. And we can, as we practiced before, we could Google it. And in particular, let's take a look at the SHA-256 hash. Excellent, Andrew. Let's see, I think this one will work. Nope. Yep. All right. So SHA-256 is a well-known hash function. And let's experiment a little bit. What should I hash? I guess we should start with potato, huh? All right. So what are you noticing about this here? Could do something else. Do breakfast. So as I'm typing here, what can we observe? What are some things that need to? Hashing loses information. Potentially, Matthew, what is a test that we could do to determine if hashing loses information or not? Because right now, it could simply be encoded because there are more bits in the hash than there are in the value. So we could do more and confirm that no matter how much we put here, it's always 64 characters long. So we are losing information. The end result is hex coded. John has it. Jason, it's being encrypted. It could be, but with encryption, we don't lose anything. So it's similar to encryption. Colin is seeing that it's always the same number of characters. Mally brings up a good point, is you can turn a potato into a hashed potato, but you can't turn a hashed potato back into a potato. I'll make a deal. Hold on. Let's do this. I'm going to stop sharing my screen for a second. If anyone can tell me, and this is on video, this is on video. So hold on, let me do, let me make sure. If anyone could tell me what string I did to get that hash, I'll give you $1 million. Guess away. So again, as Mally said, they're one way. A good hash function, which not all hash functions are good, but a good hash function will be one way. You can't go backwards. You can't turn this into the original data. But if we refresh the page, you can very quickly check what is also happening. Every time I do this, yeah, the turnip salt, it occurred to me that someone might guess something like that, and I needed to put something really random in there. So repeatable results. The hash is always the same. Close, Jonathan. You'll remember this day as the first time you came close to being a millionaire. But yeah, always the same output. It's deterministic. No matter what, it's always going to be the same result. So what if I wanted to store data in here? What could I use this for? Passwords could be a good thing. Exchanges. Ah, yes. Michael has a very important thing, very important part of this. If I change one character here, even just by a little bit, so if I change this P to a Q, how different is the resulting hash? Completely different. So this makes them useful for a lot of things, one of which, as I think a bunch of you have mentioned, SHA-256 is used for security. What about SHA-1? The original SHA hash. That's not good anymore. That's been cracked. It's broken. Don't use that. So there's a couple of cool things that we can do with this. But let's say I want to do something. I want to make a data structure that has O of 1 lookup time, and I want to be able to access the data by whatever I want. So I want to be able to say, well, this is convenient. We'll type here. No, let's go back to here. I want to say I'm going to store a bunch of numbers that are phone numbers. Let's go back and look at this level, the bucket level. I want to store a bunch of phone numbers. So will it work? Say, all right, I'm going to store my mom's number here. So 555 123 4567. So I'm going to remember my mom's number is the 0th index, and then my dad is the first. My brother's the second. Is this a good way to store things? What would be better? What would be a smarter way? We can store Jenny's number. You know, for all of you youngins out there, someone's phone number wasn't a given. It used to be something that you had to go through lengths to get. Now you kids with your internets and your Twitters and your Instagrams. Anyhow, this is a terrible way to store phone numbers, right? Did I put my mom's number first or my dad's number first? I can't remember. What would be a much better way? What data structure have you used before? Keys, right? A dictionary. A hash table is what these all are. But you've used a dictionary before, right? Or an object in JavaScript, maybe. I can't remember how Swift does these. But wouldn't it be much better if I could do something like this, like phone numbers, mom? Does this look familiar? Phone number, dad. That's a much better way to store and access these, right? It's a lot easier to work with. What if I meet someone new? Where do I put them? Do I put them in 7? What if I could say phone number, this should probably be named phone numbers, dot add. What would I do to add a new number here? What would I need in my dot add function? A key and a value. Friend is the key, and their phone number would be the value. That's way better. But this is a great system. It's useful. We all use it. But what has to happen for this to work? What do we need to do? Well, that's how we're going to do it, Matt. But what we need to do is we need to figure out how we're going to store this. And I don't know about you, but I like having my cake and eating it too. I want everything to be perfect. So I want to store all of this here. Let's do 1, 2, 3, 4, 5, 6, 7, 8. Let's do 8 for now for the demonstration. We'll make, let's use this fancy orange color. I like that. So what's the most efficient data structure to access elements? Well, Bobby, you're not wrong. That's not the answer I was looking for. An array, if you know the index, right? So what we can do is we can use hashes to turn our key into an index. And the way we do that is we'll go here and we'll hash mom. And that results in it results in a hexadecimal encoded string of 64 characters. But what is that hexadecimal string of 64 characters if I want it to be? What else could this be? A duck if I want, sure. All we need is a way to interpret it as a duck or a string or a number. And if it's a number, and for this demonstration, let's see if we can do a fancy calculator. Actually, I haven't done it this way before. I don't know if this is going to work. Let's try straining Google. What could I do if I want this number to turn this number into a number between 0 and 7? What magic operator can I use? Modulus. Thank you, Laura and Christian and Bobby and Jerry and Allison. So I don't know if Google knows how to do this, but we're going to find out together. Nope. Let's see if Wolfram Alpha can help us out. I've always been disappointed, but sometimes it works spectacularly. Sometimes it loads slowly. Sometimes pasting doesn't seem to want to work. Wolfram Alpha was started as kind of like a Google for mathematics. All right, I like how we're doing it with web stuff. So let's do web technology. We can find Google tools to help us figure all of these things out. So let's try hex to decimal converter. Here we go. Get rid of that. And it can only do 32. So let's try another. Okay. So this is a decimal value. And then we can take this decimal value, which is a very big number, isn't it? We can do it with something other than SHA-256 as well. But now Google will know how to do this gigantic number, modulus 8. No, it doesn't. Google, you're disappointing me. All right. Let's give it a number it can handle. So 2. So then, what can we do? Ask Jeeves. So we can put it here. So we can put that first phone number right here. 555 123 456 7. All right. Then we do the same thing for dad. We convert it into a number, modulus it by 8, and it goes in 7. So 1, 0, 1, 2, 3, 4, 5, 6, 7. That was 5, 5, 5, 3, 2, 1, 1, 2, 3, 4. So what happens when I will want to look something up? What do I do? Hash the key you want, modulus it by the size of the array, and then go to the corresponding index. Really tricky question. What's right here? I'll highlight it blue for a second. What's currently stored here? Whatever was already there. So it's an array, right? But what makes it different? Why are we allowed to have empty spots in this array? Although really, again, nothing is ever empty. So this has 42, this has duck, this has smell of rain, this has purple, this has elephant. And this has, can't think of anything else silly, so I'm just going to put 1. Why is it allowed? Why is it okay to have gaps in a hash table but not in an array? Because of how we access it. We're only accessing it with known keys. So let's take a look at some code. Right, hash tables are not contiguous. All right, going back to here, we're going to need to make a new folder called hashes, and a new file in it called hashes.py. We're going to import hash library. And let's do some things to experiment a little bit. All right. Give everyone a moment to get ready here. Phone numbers is an array with size of phone number times capacity bits. So not quite. There's a couple of things that we're going to talk about. One we're going to talk about tomorrow, which will probably happen now, is the possibility of a collision, which we need to handle. The other thing is that a hash table is not going to be full. We need extra space to avoid collisions. But it's an excellent question, but let's hold off on that one, Matthew, for just a little bit, because tomorrow we're going to do a deep dive into that possibility. All right. So let's do an experiment. Let's do for I in range of n. Let's be good programmers. Let's start out with a key. What is this right here? What tricky thing have I done? I'm sure you're probably familiar with F strings, but what does the B mean? Beyonce. Binary, bitwise, close enough. It means it's a byte string. It's a bytes-like object. Because what is, tricky question. In Python, what is my string? It is not ASCII or Unicode. It's an object. There's other metadata involved, other functions involved. And so what the B does is it strips all of that away and makes it into a byte string, which is important for the hash functions because the hash functions require a bytes-like object to hash. So if you want to hash a string, you have to do this. Does anyone know the other way that you can do this? Another thing in Python that you can do, which I'm noticing more and more, Python is getting more than one way to do things, which is kind of against the zen of Python, but is the nature of life. You can also do .encode, and that'll turn it into a bytes-like object as well. Or you can encode it in different specific types of things like TF8. All right, so let's do an experiment. Let's do for in range of 10. Oh, thank you. Yes, it is encode, not end code. Thank you, Michael. For in range 10, let's do hashlib .sha256 of my key. All right, and let's print that. So again, before I run this, I don't know why it's mad at me. This should work, unless I've gone crazy. Before I run this, oh, thank you. Thank you, Daniel and Ty. Before I run this, what did we talk about a couple weeks ago? What should we do? We're engineers. We think scientifically. We take a deliberate approach to things. So from what we've learned, what are we going to expect is going to happen here? Should print the same hash 10 times. Matt says, Ty agrees. All right, well, let's try it. CD into the right folder. Python 3, hashes.py. Oops. Well, what has it done? It's given us a memory address. Because, Michael, weird things happen sometimes when you use the run button, particularly when you're importing external files. So it printed the location 10 times. All right, what can we do to fix that? Call the string function, maybe. But what needs to have happened, Derek? Let's do this. Let's dig into this a little bit. Because we have tools at our disposal to help us learn this. We don't have to guess. We don't have to stab around in the dark. We're programmers. Let's program. So let's say hashed equals that, and put a breakpoint. Run it again. Get this out of the way. So hashed is that object, but how can I find out what's in there? Use directory. Okay. And what does it have? There is a string function in here. Look at that. So we've confirmed it's there. Has a name. Let's see what's there. SHA-256, okay. About, we do it that way? Nope. It's gonna make us type the things, huh? Probably helps if we type them correctly. Still that. What is this one here? So one of the things that you learn as you get more and more experienced is you start to realize connections and make, while it's not an absolute guess, it's an educated guess. And I know that I'm trying to turn this into a hexadecimal string because that's what I'm used to seeing them before. And I see a function or a property called hex digest. Well, let's try that one. Hash.hex digest. And there we go. Found it. So it took a little digging, but it's in there. The data is in there. And why is hex digest here? Why does it have this? Does everything have this? Is it guaranteed? No. Someone somewhere programmed that function to exist. Like this. So if you just try it by name, it tells you that it's a built-in method and you need to call it like a method. All right. So Q will quit. So let's get rid of this. This might be useful. So let's create the variable up here and we'll print hashed. So now we're expecting, we have to actually call .hex digest. Now we're expecting the same hash 10 times, right? All right. So that was what we expected. It's working that way. What about, let's try another one. Might have heard Python has a built-in hash function. The hash of the key. All right, so what are we expecting now? What should happen when we run this? Several people are typing. Print the hash key for both loops 10 times, 2 hashes repeated 10 times. All right, we've got a theory. That works. What should happen if I change it to string 2? They both will change. All right, cool. So, wait a minute. What was that? What just happened here? I accidentally ran it again. What's going on? It's only the second hashes. Let's comment this out. Yeah, Michael has it. I have not lied to you, but the implementation of hash uses a different seed. So every time you run it, it will produce a different hash. Now that hash will be the same for each time, but this can get very confusing when you're debugging. All right, one last question. What if I want to do what we were talking about before, accidentally? I know, it was just my fingers slipped. So again, if we were doing phone numbers, this is mom's phone number. And I want it to be an index in an array that I can access. Then I just need to modulus it by whatever the length of that array is. So Allison, that's an excellent question. I think we've talked about this a bit already, but is it possible for a computer to generate a random number? It's not. Unless you use external analog data, which is the asterisk that Michael is talking about, it's not possible. So what these functions do to create pseudo-random values, and in particular, a good hash function will generate a cryptographically secure or quality pseudo-random value. It starts out with a seed, which is just the starting point. And that could often be the timestamp or something like that. And it helps prevent determining a pattern and cracking it by using and storing historical values. So if we do modulus 8, then we will always get, ooh, that's a good one, Matthew. I like that one. So by doing modulus, then that gives us our index. So your homework for tonight is to do the first part. Hashtable.py is going to be a 2-day process. Because I just arbitrarily decided that we're going to start out making 8 space in our storage. But what's the obvious problem here? What could happen? And we're going to worry about this more tomorrow, but a collision. We could have 2 strings that have the same hash, and we're going to need to deal with that. And tomorrow, that's what the lesson is about. We're going to talk about collisions, why they happen, when they happen, and how to handle them. But for tonight, the first part of the implementation is to do all of the functions of hashtable.py. And if you have a collision, just print a warning. All right, so you won't be able to pass the tests now. You're going to have to write your own tests, which I recommend doing down here in main. Replace this. Yeah, it's possible to do 2 Jennies is another thing that could happen. All right. What questions do you have? Sorry for running just a little bit over. Take a look at the tests. Just know that you may not pass all of them because you're not handling collisions. And for those of you who do get ahead, right here is a big hint for how we're going to handle those collisions, which should look familiar to you, I hope. Yep, it's a singly linked list. All right, well, if you have more questions, when you have more questions, as always, the process is work on it for 20 minutes, ask in the help channel, then escalate to your team lead, then section lead, and then I'm always here if need be. Otherwise, have a good day, happy Monday, and I will talk to you all later. Bye-bye.